spatial data are everywhere, and somehow we have to go from representations of what the Earth actually is to models that allow these data to be collected and stored in our computers. And so we think about this on two levels. We think about conceptually, how do we think about the world, and how does that allow us to kind of come up with models for storing the data? And we call these conceptual models, and we usually talk about two kinds. One is an object-based model, and the other is a field-based model. So first I'm going to talk to you a bit about object-based models, and then we'll move on to field-based models. So object-based models really consider the world to be kind of buckets or different kinds of components that can be thought of as representing everything on the Earth. So you would think of a tree as an individual object. You think of a building as an individual object. It's almost like thinking about the world from the perspective of Lego. You have these different blocks that you put together to build a representation of the world. When we talk about things in an object-based model, we usually, like from a practical standpoint, we put the data in the computer as either points, lines, or areas. So let's talk a bit about each of those. So points are things that we use to be really honed into a particular location. So for example, we might look at hospitals or different kinds of services as points. You can kind of think that when you are navigating with Google Maps, you're navigating between your location and another location, which is often represented as points. Oil wells, that would be another example of something that could be represented as a point. It's a very specific location. Things like trees could also be represented as points if you're doing any kind of sort of natural resources work. You might represent trees as points. What kind of things would we represent as lines? So lines are often associated with roads, so things that are linear. Streams are often represented as roads, and sometimes we put a bunch of lines together and we call it a network. So when you have a line file that shows that things connect and that things might flow between the lines, then we think of these as networks. But the most common is roads and streams, I'd say, that we use lines for other things. Like if you were hiking and you wanted to look at the route that you took, you might represent that as a line on a map as well. We often I've done a lot of work with telemetry data where you have a wildlife that has a GPS collar on it and it moves around. And this is interesting data because we get GPS pings that occur at particular locations. So these are actually points. So we would say, at noon, the grizzly bear that was wearing the collar was at a particular location, and this is the point that represents where that location is. But we collect a lot of those, so if we collect them every 15 minutes, we might actually convert those points into lines. So points are the simplest form of spatial data, but when you have lots of points, then you can often connect those together to make a line. The next kind of object data that we typically use is areas. So anything that can be you can draw a boundary around would be a good thing to represent as an area. So it's like a line that closes. It starts and ends at the same point, so it kind of completes. And you can color within it and know where to stop. So census blocks, districts, zones, all of those things are good examples of areas. But also some things that if you zoom in really close, you might represent as an area could be represented as a point when you zoom out. So an example might be a building. If you have a very detailed map, you could see the whole boundary of a building and you might draw that as an area. But if you were looking at a really zoomed out version of a city, your buildings might not have enough detail, and so then you might represent those as points. So I think it is interesting to think about how things on the ground could be represented with points, lines, and areas, and how you might change this depending on the scale or the zooming in or out of your view of your mapped area. But at a conceptual level, if we map things as points, lines, and areas, we are able to identify sort of definitive objects, and we represent reality as a bunch of different kinds of objects that we can put together. Now, another way of thinking about the world is as a field, as something that is continuous. So these are things like air, anything measured in the air, anything measured in the soil. It's really hard to draw a boundary around good air quality or around oxygen. Like, how would you do that? So these are things that you could measure at different points, but they actually represent something that is continuous. Now, the way that I find it easiest to think about whether or not I'm looking at something in the world that is best represented as an object or a field is using the pencil test. So I imagine that I have a map in front of me, and if I close my eyes and put my pencil down anywhere, when I open my eyes, if I'm guaranteed to have a value under my pencil, that means I'm dealing with something that should be represented as a field. So what are things that you would be guaranteed to have a value? They would be things like air quality, elevation, different kinds of soil nutrients, anything like that. For sure, no matter where my pencil lands on the earth, I'm going to have a value. If I'm looking at buildings, well, if I drop my pencil down, my pencil might fall between two buildings and there would be no value there. And so in those cases, I have something that's more appropriately mapped as an object. It often, you'll make a decision about whether or not to use a field or object model depending on the type of applications that you're working with. So we see in cities, object models tend to be kind of more common, whereas in natural resources or any kind of environment application, we do use a lot more of the field model. It also depends sometimes on how your data is collected. So if you are using data that's collected from satellite imagery, you often end up working in a field model. But just like how object models have points, lines, and areas, field models also have different ways of practically implementing the field model into a computer. We tend to think of a field model as something that's tessellated. So you do need to have your area represented continuously, but you still have to have some kind of geometry to store your values in. So tessellations are things where you cover the surface of the earth in a single repeated shape. And probably the most common is just to use a square, so a repeated square. So if you ever work with Landsat imagery, all of your data is stored in squares that represent an area of 30 by 30 meters. Increasingly common is the use of hexagons. So I think it's Uber that uses hexagons for all of the mapping that they do. And hexagons are nice because they have really great geometric properties, which allow us to look at how space is connected in an interesting way. But those are the two that you'll see most commonly. Though you can also, you can use a variety of things. So the other common one to use is triangulated irregular networks or different kinds of triangles that you can create between your point locations. But let's just think, using kind of the most common one, the rectangular raster. How does that work? So typically we use the raster. We use rasters because they're an easy way to store and deal with mathematical data. They're pretty efficient. But here's an example where we have a image of forests, and if you dropped a raster on top of that, you would have a bunch of squares. And then within each one, you could collect data on something like, say, soil moisture. So you would imagine that in each square you had at least one sample of soil moisture, but you could also have multiple. You could have 4 or 5, and you could store in there an average value of soil moisture. And you could also include a standard deviation of soil moisture. So you could have a number of different things stored in that raster about soil moisture. When you do something like a triangulated irregular network, what you usually do is you start with all the sample points. So rather than average values within a rectangle, you could have, in this instance, 6 locations where you've sampled soil moisture, and then you just connect the points, and this creates triangles so you can store the information within the triangle. So you would take the average of the 3 points that make the triangle and store the value into the center of the triangle effectively. This is nice when you have samples that are collected where they're very dense in some locations and very sparse in other places. So you can actually represent sort of how dense your sample is, how much sampling you have, and you don't have to lose that information. We tend to use tins for things like elevation. It's quite common. But I would say those are the 3 most common kinds of ways of representing fields, is to either use a grid, a hexagon, which is growing in popularity, or to use this sort of tin environment. So then, just to summarize, let's think about how we go from the real world to getting data in our computer. So first, we conceptually decide, are we dealing with a bunch of objects, or are we dealing with something that is better represented as continuous? If we're dealing with a bunch of objects, consider, depending on the scale and the properties of what you're mapping, if a point, line, or area are best. And if you're dealing with something that needs to be represented continuously, you'll typically use a regular grid that's squares, hexagons, or tins, triangulated irregular networks.